Okay, hello everybody. I'm happy to have you here today. My name is Sophie Knöttner. I'm a research engineer from the Austrian Institute of Technology. We are a non-university research institute, and in my daily business, I deal with mathematical optimization to find decarbonized energy supply systems for industrial production sites. And I will give you a short insight today of this method and how we can use it to integrate heat pumps, especially high temperature heat pumps, in future industrial energy supply systems. So it's not a big surprise, but we see all sectors facing the challenge that they need more sustainability. And especially for the industrial sector, there comes up the challenge that clean, affordable and green energy is really a key criterion to remain competitive. However, beside the challenge, there's also an opportunity, and such opportunities come up with new technologies, and especially the high temperature heat pumps build such new possibilities, opportunities for industrial energy supply. However, in the last years, the method of mathematical optimization, often also called mathematical programming, developed to be a solution, a support for decision makers, especially to build up a good knowledge base and a good feeling for how can my energy system look in the future in my production site. And therefore, I will give you a short insight in how I look at industrial energy supply systems. So one thing I always need to consider in my work is that the industrial production site has requirements from its core process. So as long as there is not enough energy to produce whatever they produce, it will not happen. And therefore, the remaining, the quality and ensuring the quality is a key criterion, and all cooling, heating and power demands from the production process must be fulfilled. Furthermore, we have established technologies that might still be feasible and operated in a decarbonized way, but others might not be anymore. And we have new components that can join the supply system. All this together brings up various strategies for decarbonization. Just to mention a few, fuel change is a common strategy, but also electrification and their heat pumps pose a big potential. So I usually look at my industrial energy supply system in different layers. The most inner layer is the production process itself, with its cooling requirements, its heating requirements, temporal resolution of those requirements, and also power requirements. Then we have on-site supply. Typical examples nowadays are combined heat and power plants, gas boilers, chillers if you need to supply cooling processes. But also heat pumps are becoming more and more an option for those energy supply on-site technologies. And then you have the outer world, the off-site energy supply of a company, including grid connections to gas grids, to electric grids. Maybe regional renewable energy supply options need to be considered. So this is the field where I have to move and where I want to bring heat pumps into future energy supply systems which are decarbonized. I will stick to that picture to come to the optimization applications that we're usually looking. So maybe some background about mathematical optimization. In general, it is understood as the process of finding an optimal solution, optimal values for different variables for a defined target criterion under restrictions. So to give this a little more hands-on, what are optimal values, optimal variables? Typically, these are capacities of units or how they are operated at any point in the system. Is a unit offline or online? What are typical target criterions? Usually when we deal with industrial energy supply, the target criterion is always costs that needs to be minimized. Sometimes it's maximum output, but the most common criterion is costs that are minimized. And the restrictions I mentioned, these can be technical restrictions, for instance, operation ranges of heat pumps, also the operating parameters of heat pumps, but it can also cover economical or ecological constraints, such as a requested decarbonization in a system. So I can request a system to be fully decarbonized and see if the superstructure, the options of technologies that can supply my system can fulfill that criterion. So what we typically distinguish as well is what is modeled, so what is the industrial application that I want to have a look in, and how is it modeled? Do I use linear equations, binary variables, or do I do it with heuristics? I mentioned here 4 typical industrial optimization applications. Let's start with the one in the top left, the design optimization. In such models, I get information of how big a heat pump would be that I integrate, or also which sources and sinks should be combined. In operation optimization, I usually get for a given system the optimal schedule for all energy supply technologies. What I often do, and what the example I have with me will later be, is the combination of design and operation optimization. Then we have the heat exchanger network synthesis, here shortened as HENS in the middle. This is usually an extension of the pinch method, where you combine heat sources and sinks via direct heat exchangers, heat pumps, or thermal storages in a temporarily resolved model. But it usually doesn't cover the outside world. So if you have fluctuating energy prices, fluctuating requests from outside, this is typically not covered in such heat exchanger network synthesis models. Therefore, combinations of those examples here shown can make sense. A fourth example is the scheduling. This is usually reordering of production tasks. So for today, I will not cover the hands on the scheduling anymore. I will stick to design and operation optimization. And now I would like to show you what role it can play in a way from I have a question, how can my decarbonized system look like, to I have a solution, that's how I will produce my energy in the next 10 years. So we have different methods that we can apply, also different methods that we apply at AIT. And in my understanding and how I see optimization models is that it's always a starting point. So when I have a lot of questions, a lot of options open, I would go for the optimization model, which can help me to support the conceptualization of the site. A really big advantage of mathematical optimization is that you can consider technical, economical, and ecological aspects at the same time. And therefore, you can answer several questions within one model that is built. Once I have a good idea of what technology will be included in my model, will it be a heat pump providing hot water, or will it be a heat pump providing steam? Will it be a heat pump and a mechanical vapor compressor? Then physical simulation models are typically the next step. You see already that there is that iterative circle between optimization and physical simulation. So what we often do in our daily work is that we combine those two approaches and make it in an iterative loop to improve both the optimization models and the assumptions we can take for our physical simulation models. After that process, and that's typically when our work at AIT stops, detail engineering is the next step. So what happens regarding the accuracy and the level of detail? It typically increases from the optimization model, which is a simplified model compared to the physical model and the detail engineering. But what also happens is that the size of the considered system that I look at decreases, so increase in the other way. I have now some more details about the questions we can answer, and then I will show you how big such a system can be in optimization models. I brought up an example from pulp and paper sector, where we set up a really comprehensive model with a lot of components, and I think this will explain that increasing size of considered system for the optimization model best. So typical questions our customers ask us when we start working with them together, industrial partners for instance, is how can industrial energy supply at my site be decarbonized? Can it be decarbonized for 100%, or is it just a part-wise decarbonization? And another question is, how can heat pumps contribute to that? And when I integrate 1 or 2 heat pumps, where should I integrate them? Where do they bring the most value for me? Where are they most efficient and most feasible? Brings me to the next questions. People have often different sources, different sinks, and they want to know how to combine them best. And typically, also a question that comes up in the later stages, how can heat pumps fulfill my flexibility or my fluctuating demands? So how flexible is the new energy system with the heat pumps compared to the old one? Can I fulfill all those requests that I have there? So this is typically a pure operation optimization example, but within the whole chain, we often combine design and operation optimization to answer those questions, typically with one exhaustive model. I already said I will bring an example for pulp and paper. I know this picture is big, so let me go a step backward and tell you how it came to that picture. So we have our optimization models as Python code. We have all components that are shown here in that nice visual way, written as components in Python. All of them have technical constraints that they consider. They have inputs and outputs where I can connect them. But the drawback is that you need to have a lot of experience to apply such models. And what we did here, we had a project with 5 industrial partners from the pulp and paper sector, and we brainstormed with them and came up with an exhaustive list of what are their supply options for energy sources, here on the left side, so solid fuels, liquid fuels, electricity, heat. What are their typical examples? So you see here a lot of boilers, turbines, so typical CHP plants, and we came up with a lot of new options. So some heat pumps here. We also have geothermal energy here, which is not applied in Austria at the moment for pulp and paper, but might be an option. And then we have the demand side. So we have processes here that can be parameterized to represent paper machines with electricity and steam demand, but also wood grinders with pure electricity demand. And what we often have is that pulp and paper sector is not just an energy consumer, but also producer. They often provide electricity and district heating to other customers. So this is all pictured here on the right side. And with that model that we set up here, we made it available that we have a user-friendly graphical interface that can be used by non-optimization expert. It is realized as a web tool actually, and by clicking on all the components, you can parameterize them and therefore set up your system in a way that it represents your reality to a really good degree. It is customizable, so we have different users that can specify their systems and then calculate their scenarios. They can vary energy prices, they can vary a request for decarbonization. So we can say, just find a cost optimal solution, don't care about decarbonization, find a partly decarbonized solution or find a fully decarbonized solution. It was originally configured for pure paper factories that just produce paper, but in general, it's suitable for all type of plants within that sector. So what are other factories in that sector? We have pulp factories and we have integrated factories producing both. And the technologies chosen that are included in that system are based on current structures and various possibilities for future energy supply. What is the outcome of that model that we have here in the back end regarding heat pumps? So what are the insights? We found that when heat pumps are integrated, they're typically substituting CHP plants in this sector, which brings often a problem that the energy provision on-site, so the electricity and steam provision on-site, is switched to an electricity consumption from outside. So this sector actually sees a lot of organizational and cultural changes when it comes to heat pump integration. We also found that there might be economic frame conditions where the heat pump integration can be driven just by economics. Actually, we don't see them yet in Austria, nor in Germany, I would say. But the energy price, especially the ratio between the fossil fuels they use now and the electricity, is a high driver that it is economically feasible or not, and the process parameters. So actually, the adaptation of steam temperatures and pressures that are requested can really support the integration of high-temperature heat pumps, steam-providing heat pumps in that sector. However, economics are still an issue, but if you request decarbonization in a model, then you see that heat pumps are really among the top technologies that provide the system in a most cost-efficient way. So if we have the following two frame conditions, heat pumps are typically most cost-efficient decarbonization solution. First, a sufficient capacity and connection to the electric grid. And second, the absence of biogenic residues. So depending on the type of sector, you might have a lot of biogas, sludge, reject that you can use as an energy carrier. In that case, the heat pump is also good, but not as feasible as such residual boilers. But still, heat pumps will be for sure an option in the future in the pulp and paper sector. I brought some more really short examples from other sectors. So I talked already about pulp and paper. Typical sources we have there are wastewater, humid air, and we need steam. So we have high temperatures, but we showed in our models that we can reduce the CO2 even up to 100% and reduce primary energy consumption up to 60%. Furthermore, for the food sector, we had a similar project, and we found that there we have different sources. We have typically wastewater, but also excess heat from chillers. And we have lower temperatures regarding the sinks. So we also have cooking processes below 100 degrees. And there we found in a project for a specific site up to 50% CO2 reduction with a payback period between 7 and 8 years for industrial heat pumps. And the third example I brought is the textile sector. Sources and sinks are similar actually to pulp and paper. However, they also have washing processes, which makes it a little easier. And we found there that up to 70% CO2 reduction was possible, while the operating costs could be reduced. So what can I summarize? I just showed you an example of how such models can look like and how heat pumps could be integrated in the pulp and paper sector. But in general, that method is applicable also to other sectors. Something that we need for the optimization is, I think you remember the big picture with a lot of possibilities, a lot of technologies. We need a really good comprehensive analysis of the site before. But if we have that, we can get the following advantages. We understand what are the interactions and the dependencies in decarbonized systems. We can identify beneficial combinations of heat sources and sinks. And that's, for me, a really big thing is that we can simultaneously consider technical, ecological, and economic aspects. So for now, I'm finished. I'll be happy to answer your questions. And if you want to try the tool yourself, we have it at our booth in Hall 4A. And it's online. If you want, we can play a little around and I can show you how you could also apply mathematical optimization to your problems maybe. Okay, I'm happy that you joined today and be happy to answer questions.